Good morning. We'll be starting in a minute or so. So if you have any questions in the meantime, please let me know. I won't be sharing my video this morning. My internet bandwidth is not great today. So we'll be just seeing my screen or presentation, and hopefully my voice. You'll be hearing it. All right. Any questions from last time? Okay, perfect. So if there are no questions, we can continue. If you recall, on Monday, from Monday, we started to discuss how we can actually define the syntax towards the abstract syntax of a language. And we said, hopefully we need to use some powerful or expressive grammar to describe such a thing. And we have explored a few things, and we have seen that a CFG could be a context-free grammar, could be useful for such a thing, but it actually brings difficulties in terms of how to parse, how to verify if an instance actually following the intended syntax, and also at the same time to come up with a parse tree so that we can actually associate the meaning, the actual meaning, programmatical meaning, the meaning that we want to actually achieve, the operations that we want to achieve. And that would be will require some sort of or if we have a parse tree, we could do that, and we discussed that kind of briefly. Now, what I want to do is I want to go back a little bit to this concrete versus abstract syntax that we have been discussing, and then kind of touching on the topic back and forth a little bit. But let's discuss this in an example, more concrete example, where we can actually see what concrete syntax is and an abstract syntax is. So the best thing that we can, or best place where we can actually check this or explain this, is expressions. And everybody knows expressions. Expressions are coming from kind of math with some theory behind. So let's take the arithmetic expressions, for example, right? So if your language has arithmetic expressions, and almost all languages will have it, how would you actually, what is a concrete syntax and what is abstract syntax, right? So concrete syntax for an expression in the context of an expression is how do you write that expression? How do you write it, regardless of meaning, right? So how do you write it? How do you write the expression? And different languages might have different ways of actually expressing expressions. And there are a few different things that is around. For example, the regular one that we know of, this is, we know from our probably since our grade school, maybe, and that's still a grade school, but since middle school and heavily on in, what is this doing? Why is this not working? Okay, this is somehow not working. So this is an expression, arithmetic expression that we know of and we use regularly, right? So this says that I have some value in A, some value in B, and some value in C. I am multiplying B and C and adding A on top of it. All right, so this is the way that I write it is A plus B times C is this concrete syntax. And then the meaning of that, what it means when I write this, what do I do actually in the background to, let's say, evaluate this expression is the abstract syntax. And in that case, I know that from at least our common understanding in math is that this would actually, B and C will be multiplied, whatever their values are. And then there will be a value added to it. So this was not obvious in the concrete syntax. Concrete syntax says that I have an identifier, I have a plus sign, I have a star sign, and I have three different identifiers here. So I can take an identifier followed by a plus sign, another identifier followed by a multiplication sign or a star, and then another identifier. So this is the concrete syntax, whereas the abstract syntax is, what does this mean? What do I get out of it when I actually, let's say, communicate to my computer or communicate to, let's say, in this case, we are communicating to a CPU. What would CPU do with this thing? And the meaning of that is, again, as I explained. Now, there are other alternatives to actually define this concrete syntax. It's not supposed to be just A plus B times C. The same meaning, the same abstract syntax can be expressed in another concrete syntax, like this, what is called reverse Polish notation. So in the reverse Polish notation, it's very simple. So what you do is you start with your variable, with your values. You say a value, in this case B, another value C, and then you have, if you have a, let's say, if these are followed by an operator, in this case a star, then I know that I will be actually multiplying B and C. And then I'll have another value, A, and then followed by the plus sign. This will say, okay, now B and C was multiplied, and I have a temporary value at my hand. Then I will have A added to it. So this is reverse Polish notation. And these two types of notation, or there are actually other notations as well, for expressing concrete syntax for arithmetical expressions. We have alternatives. You can design on your own. There are not many possibilities, but you can design let's say a foolish syntax that actually, concrete syntax that actually can express similar things. Here, the important thing is that regardless of the abstract, the concrete syntax here, our abstract syntax, the meaning of this thing should be the same. So there should be no ambiguity in interpreting the meaning, right? So usually for expressions, we have what is called this expression tree, representing the abstract meaning of an expression. So if you have an expression tree for expressions, you can get the meaning of the this abstract syntax, the meaning of this expression. You see an example here. If you are able to actually, from this concrete syntax, if you are able to go to this expression tree that I have here, this one here, this guy here, then the meaning of this is actually can be easily extracted with a, let's say, a bottom-up type of a, let's say, evaluation. So in order to do this one, you need the value here and the value here, but the value here is not available yet. Therefore, you need to actually evaluate this guy. That means that you have to have the value here and then value here. So once you actually are able to evaluate this one, you can go and evaluate this one. So there is no syntactic, there is no, once you have this expression tree, there is no problem in actually getting the meaning or the calculating the value that you want to actually have, the abstract syntax of this. Now, it is, however, not clear that from, let's say, going from here to here or from here to here, this is not clear if you can actually get to a, let's say, concrete expression tree or a unique expression tree, sorry. So you need it for define the concrete syntax. But the question is, if I start from A plus B times C, do I get to this particular expression tree? All right. And the answer is, it's not clear how you would actually get to this one. It may be possible that you would actually do A plus B first and then do a multiplication, meaning that my expression tree could have been, let's say, something like this, right? This is a plus sign, this is B and C, and this is B, A and B, sorry, A and B here, and this is C. So this is an alternative 3. Now, if I have two alternative expression trees, in this case, this means that my meaning, abstract meaning, is not unique. And we said we wanted to have a unique meaning because otherwise the program, through programming language, the instance of this program is not going to be actually deterministic. It's not going to be it's not going to be you cannot depend on this algorithm or program to actually generate the same results given the same input. So these type of, when we go from here to here, in our language, I mean in math that we know of, the language of mathematics, or at least arithmetic, right? We have a certain assumptions related to how to convert this guy to here. And many of us will actually interpret this thing as this one here, this red one here, not this one, the blue one. Why? Because we have some assumptions that is built in. And the assumption usually is that, let's say, multiplication takes priority over addition. Why? Because this is what we have been taught. And this is maybe the unwritten rule. Maybe it's written somewhere as well, I don't know. But this is a rule that tells me that, yes, I have two options here for this simple expression in its syntax, concrete syntax. When I go to abstract syntax of it, or try to get the abstract or understand the abstract syntax or interpret the abstract syntax, I can have two alternatives, but I know which one is actually the good one, or which one is the acceptable one and which one is not the acceptable one. So you can see that these expression trees are different because the abstract syntax that is actually interpreting the concrete syntax actually lets us to have these two trees, possible trees, right? Now, this is a big question that we have to make sure that this is not the case. Now, I know how to solve this one because we know that from math, from some people decided to actually have multiplication for them is, let's say, was more important, or at least the multiplications come earlier because they have seen this one, and when they communicated these between themselves, they said, okay, what do you mean by here? Are you adding A and B first and then multiplying it by C, or you are multiplying B and C and then adding to it A, right? So they said, okay, hey, let's resolve this one. How do we resolve it? The rule, additional rule there, and this additional rule says, okay, multiplication comes before the addition. Now, the question is, how do I actually put this in writing in terms of a grammar? How do I describe this as part of a grammar? So if I were to actually interpret this, or let's say put the concrete syntax of this one, I would probably do something like this. We have seen this one, right? So expression goes to, my rules are gonna be some identifier. This is one part of the thing. An expression can be an identifier. It can be something else. Let's say it's an identifier plus another expression, and perhaps also identifier times another expression. So this could be one way of actually trying to define the concrete syntax for this thing. Now, from this concrete syntax, I have to go back to my abstract syntax. And we said the abstract syntax is going to be associated with the parse tree that I get out of this concrete syntax, right? So when you have this input to this particular grammar, it will say, yes, I can explain this one easily because A is an ID. So this would probably generate something like this, right? So let's put it here. It will say, okay, I will start with an E, and I will say this one, ID, meaning A plus E, and then E will go to, again, B times C. I'm doing some shortcut here because I need to have an E, another ID here, and an ID goes to A. So I'm just kind of shortcutting that step. Okay. So you can see that this is already similar to this expression tree that I have, right? So now, if this is the case, then I can readily actually do this one without any problem, right? So this particular syntax, concrete syntax, actually, for this, at least for this part, for this A plus B times C, it only generated one output, one parse tree, not two parse trees, right? So this seems to be okay for this one, but it's not necessarily okay. I'm not gonna continue if this is an ambiguous grammar or not. I'm not gonna come to that one. So now, if I am able to actually get to this now, if I have a concrete, or let's say one instance, only one instance of a parse tree that I can generate with this guy, then my abstract syntax can be now interpreted from this thing, like we try to do with this expression tree there. Okay. This is important. Don't confuse with what an expression tree with a parse tree, please. You do this mistake quite a bit in exams and other places. An expression tree is kind of a way to define the abstract syntax of an expression, which is useful, let's say, explaining things like this here. A parse tree is an output of a grammar for a given input, and if it is a grammar for an expression, then we can use that expression or that tree. Hopefully, we'll see later on, hopefully with some added rules to this thing, we can parse this tree and get that abstract syntax, get that meaning. But again, if we are choosing that way, that path, that we generate an abstract tree, parse tree, and then get the abstract meaning of that expression from that parse tree, we have to have a unique tree. And expression tree and that parse tree seems to resemble each other a little bit. It's not exactly the same thing. It is kind of showing the meaning of how to do the calculations, how to do the evaluation of that expression. And it is actually embedded in. So this expression tree, if it is done right, perhaps, is embedded in that parse tree. And I can actually get that meaning out of that parse tree easily if I have a single parse tree that I generate for a given input for the given grammar. Right, so this is important. So when I say, okay, do a parse tree of a given input for a given CFG, don't show me expression trees. Expression trees are only used in this context, and that's it. Be careful. Now, as I said, there are the order of traversal of the given, let's say, given, let's say, as this we discussed this one, but given expression is an important one. So you can have an this is for in-order traversals. You can have two possibilities here. You can see that. And this is for a post-order or reverse Polish rotation, right? Notation. So you have 3, 4 followed by 4. Here you have 3, 4, 5 followed by plus a minus. And what this would do is this would actually get these two first, 20, and then it will add to 23. Here it will actually go for this one first, 7, and then multiply that 7 with the other things. So you can see that both actually post-order traversal or in-order traversal can actually have the same syntactic ambiguity. Okay. So, however, the difference between these two is post-order traversal is actually if you have an expression tree, or in our case, we'll have a parse tree. From the parse tree, you can easily evaluate the value if you have the post-order traversal by using an operand stack. That means that you can actually just stack the thing. So you put, this means that you put 3, you have a stack here, you put 3 on the bottom, you put 4 for this guy here, let's say. And then when you have a plus, what you do is you actually apply the operator, and then your stack becomes only 7 here. And then you push your 5, and then when you encounter an operator, you actually apply that operator on top of that stack, however many arguments it actually has. So you can see that if I have something in this notation, the abstract syntax actually is described in this notation, then I can easily do this calculation. And this is very, very, very simple stack, right? Whereas this type of a thing, or a parse tree, would require some sort of, let's say, depth first or bottom up or whatever type of a thing, and it will be a little bit more complicated than actually a simple stack algorithm. Now, why is this so important, you may ask? Why do I care? I mean, I know I have algorithms that can parse a tree easily, And I have algorithms that can parse actually, that can do stack as well. So, but you can imagine that for complex stuff, post-order traversal, the stack-based operand stack, can actually be implemented very easily with a few line of code, and it could actually it could be very fast. Whereas the other one, expression, the tree, parse tree, or expression tree in this case, the implementation will be a little bit more complicated, maybe more time consuming. And in the past, in the 70s, time was very, very important because you have very, very slow machines that actually operates in megahertz, not compared to today's gigahertz, right? So when you have a megahertz or maybe even a kilohertz machine, you don't want to actually spend, you would probably, you would prefer a stack over a tree. Maybe a binary, but doesn't matter. So it's expensive. So one example of actually using this operand stack is the Forth language. So this is a language that is kind of quite old. It's not active probably these days. And probably one of the reasons would be that its efficiency, very efficient to implement such a thing. But this post-order notations, they are not very readable by users. So you can see that here, I cannot say, oh, B, C star A plus, what is this? But on the other hand, I know that A plus B times C, I can readily read it without any, let's say, learning. The other one requires a little bit of a learning curve. Okay. And sometimes you can have mixed expression notations as well. That doesn't matter, right? So here you can already see that you have, let's say, one thing here, and then it doesn't matter what the square root is doing, and then you have another expression here, right? So an expression tree for this one would be something like this, and you can actually do this in prefix notation as well if you want to. Sometimes this postfix notation versus prefix notation can also be done here. You see that this prefix notation, let me see, what am I saying here? Okay. So here in this prefix notation, just so that you know, this one is called arity, and it says, okay, this particular operand is operator is actually a minus operator, so subtraction, but it has it accepts one input, meaning this is a unary operator, right? So whereas this operator here is a binary operator, it requires two operands. Okay. Now, so we have postfix notation, prefix notation, infix notation, mixed fix notation, and so forth. So sometimes you have also these, like this one here. This one here actually is kind of a prefix notation, right? So, and you have the infix as well, or and then postfix. You see here, you have the postfix notation. So this actually says that the operation is applied to this one as a postfix notation, as if it is in a postfix notation. And like the ternary conditional that we have, you have a conditional expression. You have the question mark, and then two alternatives that you would generate. This is an expression. This is kind of a so you know that this is an expression, right? So this will actually return a value, whereas an if then else statement or if statement in Java or C, will not return a value. It's a statement versus an expression. This is a ternary conditional is an expression. And you can see that this is actually kind of a having postfix notation. And the thing is you have the, this is kind of a mixed fix notation. You can already see. Now, this means that as all languages, today's languages like C++ and Java and so forth, they have, they don't just go for infix notation or postfix notation or whatever. So there is a mix of actually all these things because they have useful things, and it makes the syntax, the expression of syntax, it makes it easier to do. And people know it, people learn it. And if you are, I mean, from earlier things, people knew it already when they designed Java, for example. And when you are learning from scratch now, it's part of the learning curve that you have to actually make sure that you know what a postfix notation, prefix notation, and infix notation is. Okay. So let's look at an example. If I have an expression like this, again, we are talking about concrete syntax and abstract syntax in the context of an expression only. So this has to be done later on. We are going to see that we need to do this for everything, right? So the entire program has to actually be associated with this abstract syntax. In this particular case, we have an assignment or a declaration statement, and then we have an assignment here, and then we have an expression here. This is C style. Let's think about this as C style. So for this particular thing, forgetting about the first line, the second line, when it goes through the lexical analysis, it will generate tokens. And so the first token is going to be an ID because position is an ID. Usually, when we generate these tokens, we also keep their original identifier name as part of the data so that we can actually modify that later, or we can refer to that later on and get the actual meaning out of it. And then you have an assignment token. This is this one, an ID, another ID initial, a plus sign, a plus token, another ID, a token for multiplication, and a number, this is a literal, and then a semicolon, this is another token. So these are the tokens that will be extracted once you have your lexer on this one. Lexer will go for a finite, deterministic finite automaton, perhaps here, and then it will have parts like for identifiers and for these keywords and so forth, right? Okay, so once you have this one, your the tokenized expression is going to be something like this. So ID1 equals ID2 plus ID3 times 60. This is the tokenized expression. Then here we have to be, one thing that we'll do is we'll look at this later again, but here we have, when we talk about actually this expression, this 60, number 60, has an implicit type concept on it. So we probably assign a type to it. And in this case, whatever the rule is for the language, if the language has integers and let's say different types of integers and different types of real numbers or floating point numbers, then this will be actually implicitly converted to something, unless you have a let's say a type inference system or some sort of a advanced typing system that can decide later on what this is going to be. And we are going to discuss those later, that type of typing is not an easy task to do. Okay, so the parser will parse this. I don't have the CFG here, but CFG is apparently, let's say, parsed it to this one here. Again, here, I'm not showing the parse tree, but I am showing the expression tree. I should be actually showing the parse tree, but in this example, it's easier to show the expression tree. So this expression tree, again here, you have so you have the assignment one. Since in C, assignment statement is also an expression, meaning it returns a value. This is why we got this as an expression. So you have the ID1, and then you have the +1, ID2, you have the multiplication, ID3, and then here you have an integer float number. So this is supposed to be there probably. If you don't have if you have other typing mechanisms here, you may not have this one. And then what happens is that this is after this stage, once this parse tree, or in this case, this expression tree is actually generated, then you can easily actually go from this one to an intermediate code where you can actually put the meaning on top of this. So you would do some sort of a traversal of this thing. So the traversal will be some sort of, let's say, bottom-up type of a thing. So you'll be doing the bottom part first. So this means that I need a value here. So it is integer to float 60. You can see here, this is a temp1 here. Now, temp1 and ID3 will be multiplied to temp2, multiply that with ID3 and temp1. And then the result is in temp3, so temp2, sorry. So that will be added to ID2. So this is this one. And then ID1 is going to be added to that value. This is a temp3 here, and ID1 is going to be assigned to that temp3 is going to be assigned to that ID1. So this is my intermediate code. So this is fine. You can see that I can do this automatically. Once I have this parse tree or expression tree in this case, I can actually traverse this tree and find, again, there are many different easy ways to actually do this traversal. We are going to talk about that maybe briefly later on. And then I have this intermediate code. This intermediate code is actually not optimized. You can see it already that this into float, and then I am actually taking into float 60, putting in temp1, and then I am taking that temp1, putting it on, multiplying it with ID3, and then I am actually adding on top of it this ID2, and then assigning it to that one. So this is there are too many assignments here. This has to be done, fine. This has to be done, multiplication has to be done, addition has to be done, assignment has to be done. But I have 4 assignments instead of 1. And I have the multiplication, conversion, and addition as well. So you can easily see that you can actually get rid of 2 of those assignments easily. And an assignment is the expensive thing for a von Neumann machine. Why? When you do the assignment, what you do is you take your number or value from your, let's say, current wherever, whatever you have in your, let's say, in your arithmetic logic unit. Usually you have registers, and you take those values from the registers and put in memory, and then from memory back to, when you try to use them again, you read them from memory and back to the thing. So this reading from, so if this is the arithmetic logic unit, and this is the memory, and then this is the CPU. So writing something here and reading something here is very expensive. So what you want to do is you want to actually keep the, let's say, intermediate result on the CPU, on the registers, so that you can actually do this one. And you can see that already this thing is going to be twice as fast as this one, most probably, at this from the memory perspective. And then you can actually have this one to an assembly code at the end. This is the code generator part of it. After optimization, you optimize it with your intermediate code, And then you convert this intermediate thing to, probably you have for multiplication some sort of, so multiplication is very simple. So you have FP2 in the memory is moved to ID3, and then you do a multiplication and so forth. So this is the entire cycle of coming from source code to lexical analysis, tokenized expressions, and then parser, and then hopefully parser has a unique parse tree, and then we are, in this case, we are showing an expression tree here, and then this expression tree or the parse tree is going to be used later on. We are going to see how to do that to generate this intermediate code, and then optimize code, and then assembly code. Now, we have seen that actually, if I have an expression of this form, or if I have a grammar that expresses this syntax in this form, I can already see that there are two possibilities to interpret this A plus B times C. And when I have two parse trees, which is syntactically valid, that this concrete part of the syntax is okay, they are both valid, but the way that I would implement this now using this algorithm that we discussed briefly, doing a bottom-up evaluation of this thing, these two will generate two different values for me. Therefore, my abstract grammar here is, or abstract syntax here is actually the way that I define it. I try to define the abstract syntax along with concrete syntax, or at least I want to write on the results of the abstract concrete syntax to do the abstract part of the syntax, then this will not work. This cannot work. So what can I do here? I can do two things. I can either try to remove this ambiguity within the concrete syntax here. So we have seen that if I actually did this some sort of with an ID, if I add an ID and I say ID goes to, instead of this one, ID goes to this, and these are already just IDs, and the expression should go to ID as well. If I do something like this, this is already resolved. Okay, this is fine. This is first way. The second way could be that I actually I kind of separate the abstract syntax and do something else with it, or I actually define some other rule set, maybe use a natural language to define the concrete abstract syntax. The second approach is very dangerous. I mean, it's not practical. First of all, we want to have actually kind of a unifying thing that can handle like just a grammar, and then grammar is we are able to resolve that grammar. We are able to let's say parse that grammar. I mean, implement that grammar for any input, and then the abstract syntax hopefully comes free. So now what we are saying is that let's actually separate these two and try to get the abstract syntax. Now we need to find the relationship between the concrete and the abstract syntax in this case, which will be very, very difficult to do. Now, the second approach is going to be, or the first approach, I try to fix it, or I try to change my concrete syntax such that these type of things never happen. So this would mean that I would actually I'll try to build such a grammar that I hope that it doesn't have any ambiguity. Now, then the question is there a way to make sure that there is no ambiguity? And And the answer is it is mathematically impossible to determine if a given any grammar, if a given grammar is ambiguous. There is no such algorithms, no such solution to that problem. So we cannot solve it. We cannot mathematically say, okay, I can. So what do we do then? So we do what we usually do as engineers. We come up with, let's say, we first of all divide the thing into manageable pieces. And then we try to at least make sure that from our experience and whatever, and with some analysis perhaps, and hope that simplified enough such that the grammar is not arbitrary anymore, which will come to. So there will be some set of grammars that will be easier to, or at least I can answer this question if it is mathematically possible. And then with the, of course, downside that we'll be losing expressiveness of the grammar of any arbitrary grammar that might have been there. So the answer is ambiguity is bad. There is no way that we can actually guarantee that there is no ambiguity given any grammar, but for some subset of grammars, we can detect them. We can detect them, and we can hopefully then, if we detect them, we can go and try to change the grammar, the rules of the grammar, such that that ambiguity is not there anymore. Okay. Now, this will bring me to the point where we left on Monday. So now we are going to go back to these restricted grammars with several things in mind. One is we want to make sure that, or at least I don't know if we can call it make sure, but we want to be aware of if we can actually detect any ambiguities in the grammar. So regular expressions will not have it. So, but I cannot do any concrete syntax with a regular expression or the regular grammar. So I have to do more. So the question is, where is that more? This is the first one from ambiguity perspective. The second one is also, there has to be an algorithm that can parse that grammar for a given input, or it can parse a given input for that particular grammar. We have to have that. Now the question is, we discussed this a little bit. We said there are two possibilities to actually have. One is this top-down approach for solving, parsing a given input for a given grammar automatically, or a bottom-up approach. And top-down approach, we call this recursive descent something, if you recall. And we said this is, it is what it is. And then now we are gonna look for another alternative, bottom-up parser. And for that, we need to redefine or define a little bit more formally what we discussed again on Monday, these sentential forms. So for a given grammar G, now this will get a little bit formal. With a given start symbol S, any derivation that S goes to alpha is called a sentential form, given that if it contains only terminal symbols, is a sentence, if this sentential form actually only has terminals, then it is a sentence in this language generated by G. The language that is generated by G is expressed with this term here. The grammar, and the LG is, L of G is the language instances, sentences, possible sentences that I can generate. It may be infinite. The possible sentences that I can generate with this particular grammar. So if this sentential form will be actually called if it has only the terminal symbols, then it is a sentence. It is it's an instance of that language. If it contains one or more non-terminals, if it contains at least one non-terminals, it is just a sentential form, not a sentence of L of G. It's an intermediate form. You can say this is an intermediate form. All right. So after this, we have two different form of this thing. One is left sentential form, which is a sentential form that happens in the leftmost derivation of some. So if I am doing a leftmost derivation of a sentence, then this will be called left sentential, and then the opposing one will be, or the alternative will be, the right sentential form, where if I am doing a rightmost derivation of some sentence. Okay, so I have a sentence, given sentence, hopefully part of the language. Let's say, as we said here, E goes to, what did we say? E goes to E plus E, and E times E, and A and B and C, right? So A plus B, when I parse A plus B is part of this sentence, I mean this language, right? Expressed with this grammar. Okay, and then if I am actually doing, let's say, some sort of a bottom-up thing for this one, I would have, for example, A plus B, and if I'm doing a leftmost derivation, let's say leftmost derivation would be, or let's say start from E goes to E plus E, and leftmost derivation, if you recall, should actually evaluate or eliminate or try to eliminate the leftmost non-terminal. In this case, this will be A plus E, and then A plus B, right? So depending on how you do your derivation, it can be either a left sentential form or right sentential form. And we want to do either of these two things. Why? Because we want to do this one. Leftmost would be a bottom-up approach, and the rightmost would be a top-down approach. Whatever, we are going to see that in a few minutes. So fine. This leftmost derivation and rightmost derivation, we have seen that they will actually differ in terms of how you do it. But hopefully, if you have a grammar which is not ambiguous, then leftmost derivation and rightmost derivation should actually result in the same parse tree. So derivation order should not have any effect on the language generated by this grammar. This is for concrete syntax, and then for abstract syntax, we want to make sure that that parse tree is only one, is the same. If they are if these are different parse trees, then I have a problem. Meaning, I cannot actually associate the abstract syntax to this one without any ambiguity. All right, so let's stop here and take a 10-minute break. We'll be back at 3 after 11. All right, welcome back. Let's continue with where we have left. So if you recall, last time we looked at these LL parsers. These were parsing, kind of doing the top-down parsing, left to right derivation, and left to right looking at the input. So scan the input left to right. So this is my input here, and I'll be scanning this with LL parser from left to right, and then that's it. So and then doing the derivation using a leftmost derivation. On the other hand, an LR1 is going to actually be doing still the left to right, but with rightmost derivation. So for this one, the algorithm is what we call the shift reduce parsing, and a stack implementation of this parsing algorithm. There are 4 possible actions that you want to actually have. There are when you have an input, or depending on your input, your current handle, you have a possibility of a shift, meaning you move the next input symbol on top of your stack. This is the scanning of input part. So you move the next input symbol to top of your stack. And a reduce is replace the handle. This is the we're going to talk about what a handle is in a few minutes again, but the handle on top of the stack by a non-terminal. So you have some portion of your sentential form on the top of your stack, and what you want to do is you want to actually replace that part with a non-terminal symbol. Remember, we are going bottom up, so we'll be actually getting, for example, at some point in my, let's say, stack, I might have some portions of a branch that can be formed. And so if this portion of a branch, this part is already there in this tree, then I can replace this guy with this one. Therefore, I can get rid of this part of the tree and continue with the rest of the tree. And this part, we call it a handle. And I'm going to give you a formal definition of this in a few minutes again. All right. So, and then these are the 2 actions that you do. You either do a shift, meaning you actually just put one of your data on top of the stack, or input on top of the stack, or you do a reduce by looking at on top of the stack. If there is a branch that can be actually cut off or replaced by a non-terminal, you would do that. And then there are 2 other things, possible things. One is accept, meaning a successful completion of parsing. This would mean that you have reached your start symbol, and there is no input left in your input. An error, when you have a syntax error discovered, meaning perhaps you reached an input state, a start state, you don't have any, you have still input left, or you have actually reached a conflict situation where you cannot actually decide what to do. We are going to talk about this in a few minutes. Initially, the stack is empty, all right? And at the end of input is empty, and then so when you actually initially you start with the empty stack, and then when you are done, the end of input is going to be empty as well. So now this type of this LL versus LR parsers. So the LR parsers, what they do is when you go bottom up, what you are doing is actually you started from the bottom, and when you started from the bottom, what you are doing is you are looking at actually the right hand side of your production rules, and you see them all. To replace one production rule with a non-terminal from right hand side to left hand side, doing this reduce step, you are looking actually into a larger portion of the input. Whereas when you do a LL parsing from top to bottom, you are actually trying to match a portion of your right-hand side with a production rule, only a portion of the right-hand side. So these LR parsers are more powerful in terms of their capabilities or expressive power than LR. So the parser actually repeatedly matches the right-hand side of a production against a substring in the current right sentential form. This is the right sentential form. And at each match, it applies a reduction to build the parse tree. Each reduction actually replaces a matched substring with the non-terminal on the left-hand side of the production rule. Each reduction adds an internal node to the current parse tree actually. So one of the advantages of this one is that, and the result is another, at the end of this reduce step, the result is another right sentential form. And if you are doing a shift will also be resulting in a right sentential form, because it will be only adding one more terminal to the thing, and adding one non-terminal or terminal symbol to a right sentential form is not going to change its rightness or leftness. Now, again, this one is important as well here. When you actually do a reduction, you just add it's easier to build a parse tree with this one. You just add a node, and then the tree is actually going to be built from bottom to up. So the result is going to be, the final result is going to be rightmost derivation. And of course, it's going to be in inverse. So what is this handle that we discussed? The handle is actually, what we are trying to do is, we are trying to find a substring, some substring on the current sentential form, where this substring actually is the part of a right-hand side of a rule, a production rule. And then what we do is we reduce this to this one, okay? So that we actually obtain a rightmost derivation. We call this this part of it a handle, okay? So a little bit more to this thing, and now if you have multiple handles, or let's say if you have a handle, or if you have something like, let's say A goes to alpha, this is the current handle on top of the stack, and this is also, you have also another rule that goes by the same thing, B goes to alpha. So if your handle matches two production rules right hand side, then you have what we call a conflict. You cannot choose. You can either choose this guy or this guy. This is a reduced conflict, and we are going to talk about this one. Now, a handle of a right sentential form, if you have a right sentential form lambda, is a pair that is actually A goes to the, some beta and a K, where A goes to beta is a production rule, and K is a position in this lambda that beta is the rightmost symbol. So this means that I have, let's say, I have a lambda, not lambda that way, but here it is. So what this actually does is, when you look at your input, or when you look at your current right sentential form lambda, you have some part of it is beta. This beta is a part of it at some location K. And if this handle, if this thing is a handle, then replacing this beta in lambda at position K with some A, which is the left hand side of this rule, produces the previous right sentential form. And this is in a way that lambda is actually derived in a rightmost derivation. So this is very simple. So if you have this part here, what you are doing is, or if you are actually doing this part, you are replacing this guy with this part at this location. So you are doing rightmost derivation because you are going from here to here, right? So, okay. So because this, I call this lambda, but it's a gamma. If this gamma is a right sentential form, this current sentential form is a right sentential form. This substring to the right of handle contains only terminal symbols. So this part, this W, is gonna be only terminal symbols. The parser in this case doesn't need to scan past the handle. It doesn't need to actually scan past this point. It will only need to scan up to this point, right? This is good. This means that I don't need to look ahead. I need to stop at this point. I don't need to look ahead in my input. I don't need to look for more things in my input. I need to look in my input only at this point, till this point, however many terminals I have left on the left of this beta, or this beta here. So if the grammar is unambiguous, then every right sentential form of the grammar has exactly one handle. There will be no other way. So this is the unambiguity of the thing. Now, this is actually this can be looking ahead. This is this LR parsing. This number one is how many symbols you can look ahead. How many terminal symbols that you can look ahead. So you see an example here there where we have essentially this alpha here, and then we have at this stage of the derivation between these two sentential forms, I am replacing this lambda by B when I go this way, of course, and this means that, and then this lambda is gonna go to whatever. This means that I only, lambda is the right sentential form. The substring to the right of a handle contains only terminal symbols. And this means that the parser doesn't need to scan past this point. It only needs to scan up to this point. And this would be, this is what this one is implying there. Just one look ahead. All right. So let's do an example, a simple example. So my grammar is here and my input is here. So I want to do a shift reduce parser. I have a stack. This is my parse stack here. This one is parse, and then this is each step, and this is my parse stack. And this is the current rightmost sentential form. This is the look ahead, one look ahead that I am looking. The next symbol that I want to actually consume from my input. And this is the unscanned part of the thing. This is the kind of the right part of that from the look ahead to the right. This is this part. This is this part that is not scanned yet. And then the action that I will do. So I come to, I start with an empty stack at the first step. And my look ahead is ID, rightmost center is nothing. And I have unscanned inputs, still the entire thing is unscanned. The only thing that I can do here is, do I have an error? No, I don't have an error yet because I don't see any problem so far. Am I done? No, my stack is empty. I don't have to be able to done. I should have my unscanned input should be empty, and my parse stack should be empty as well. Sorry, it should have only the start symbol. All right. So first stage, I can do two things: either shift, meaning I take one of my input symbols and put it on top of my stack, or I can reduce. Now I cannot do a reduce because there is nothing on the stack. Therefore, nothing will not match anything in this rule. So you can see that right-hand side requires either this or this for this rule, for this one, and for this one, there is no empty one. So therefore, I need to do a shift. Okay. When I do a shift, I am here. My parse stack has ID, and my right sentential form is, in this case, is ID plus, this is the part that I don't see it, right? So ID plus this. Now the question is, can I do a reduce or shift? Okay. Now here, let's say that I do a reduce because I can do a reduce, right? Why? Because I have this rule here. This says F goes to ID. Therefore, I can reduce such that now ID is reduced to F. Okay, and my sentential form becomes this. This is still right sentential, right sentential, F plus ID times ID. Can I do still a reduce? Yes, I can do a reduce because F goes to T. So this is this one. Can I still do a reduce? Yes, T goes to E. So this is the fourth step. Now, can I do at this stage? I don't have anything that can be replaced by the right-hand side, meaning E plus something. E plus T, no. And E plus, look at this one. You have E plus T. Let's erase this one so that we know where we are looking at. Either E plus T should be there. No, there is no such thing. And there is no such thing. So therefore, I cannot do any reduce. What I will do is I will do a shift. Now you can ask the question, why didn't we do a shift here? We could have done a shift. We'll come to that one in a few minutes. All right. So now we are here. We did a shift because E plus, this is the handle here. This part is the handle. There is no such thing as replacing E plus with anything there. So I need E plus T, or yeah, that's it. I need E plus T. Okay. So I do a shift. I have E plus, and I cannot do anything about E plus either. So I need to still do a shift because there is no right-hand side that actually matches E plus here. This is the only one, and it cannot match E plus. So I will do another shift. Now I have E plus ID. Now E plus ID, I can do a reduce here because the handle here is ID. ID can be a handle, and I have this one here. Okay, that means that ID can go to F, and F E plus F times ID. I still have an F here. This is my still this is in this one here. I can still actually have this one as one of the right hand side of my rules. That goes to T. E plus T is okay. Now let's stop there. Okay, now we are E plus D. Now here, I can actually go to E plus T, and then I can go to E, right? I can do that. Or I can actually do a shift and push the star there. All right. So I have two possibilities here. So the first possibility is that if I move to E plus T, let's say if I actually explore this one and do a reduce, there is an E plus T here. I can reduce it, right? Then it will go to E. and I'll have only E on top of the thing, and then I will push the next one. The next one is a star, and there is no E star here. E on the right hand side has only, with a starting E, you have only E, and there is no star. Therefore, this is not gonna help. So this is not gonna match. So I have to abandon that, and I have to do a shift here. So I do a shift, and I do another shift. Now I have ID on top of it. I can handle that one. That goes to F, and then F goes to T. Now I have the E plus T. Now then I can do now this one with this guy, because if I have E, I don't have anything left in my output look ahead. Therefore, I don't need to worry about it. So I can actually do this one without any problem. I can reduce, and then at the end I have E and empty. So output is empty, input is empty, and my parse stack has only E on top of it, and therefore this is going to be accept. All right, so we discussed this one. Now, the parse tree for this one is going to be very simple. You're going to start here. When you do a reduce, you're going to say, for the first time I reduce, I will do this one. I say, okay, ID goes to reduce. We said reduce. ID goes to F, right? Now, this is the first one here. All right, and then, sorry, where am I? And then the second reduce, F goes to T. This is the F goes to T. I'm just adding. I'm saying, okay, add a node to my tree. Assume that this is the part of the tree now. It starts from here. ID is the first thing, and then ID goes to F is the second part of the tree, and then the third part. Okay, and then a third reduce says ID goes to T goes to E. Okay, now T goes to E. It's here. Perfect. Now let's look at this one. I have this reduce here, and this reduce says E plus ID. Okay. Now it's gonna be E plus ID here. It's supposed to be this one, but this is not ID. This is the ID, E plus this. And then I'm gonna add, let's erase this one. So I go this way first, right? I erase everything. I go this one first, and then I have now this one, and then this one. Now I will grow this tree this way. Right, so this actually grows, and then it will be adding this one at the end to this one. All right, so the building of the tree by just looking at the reduce actions is very straightforward here. Now, there are a few conflicts that you can see. So this is called LR1 algorithm. One is for just looking one ahead. If I was able to look ahead 2, 3, 4, I could do more, but those are gonna be more expensive, right? So LR1 is gonna be looking ahead only one symbol at a time, terminal symbol at a time. So the generic shift reduce strategy is that if there is a handle on top of the stack, you reduce, otherwise you shift. So this is the first conflict resolution. So it says, I will try to reduce first always. This would actually, if you don't push, if you don't shift, but you always reduce when you are able to, this is actually telling that you are doing some sort of a rightmost derivation. It's clear, right? So it's always a rightmost derivation. So this is fine. So if there is a choice, if it is legal to shift or reduce, there is a shift-reduce conflict. So if you have both shift and reduce at the same time, then there is a shift-reduce conflict. If it is legal to reduce by two different productions, then there is a reduce-reduce conflict. So the conflict, the source of the conflicts may come from ambiguous grammars, may come from there. And ambiguous grammars always cause conflicts. And sometimes actually many of the non-ambiguous grammars can actually result in these type of problems as well. So one possible way of actually removing the ambiguity is you define a non-terminal symbol for each operator. This is usually coming. I mean, the best explanation can be given in the case of expressions, right? So in the expression, this type of conflicts, this ambiguity, is related to actually at the end the precedence level of the operator, which comes first, right? So if you have two options, probably you would actually, when you build a tree, when you take one option for the other one, then you are already preferring one of these operators or putting a precedence on one of those operators or priority on one of those operators that you choose, if you do it this way. The alternative is what you can do is on the right hand side of the production rule, you can try to enforce the proper associativity. So for example, you could actually introduce, let's say, into your language or into your grammar, let's say, helpers that enforce these associativities, like parentheses. Or in some cases, you can actually start with your ambiguous grammar and you can try to remove the ambiguity with some techniques. They are not. They are not. There is no generic algorithm that actually can remove any ambiguity, but some of the ambiguities can be removed. For example, in this case, what we are doing is, what I'm gonna do is this one, like this, doesn't tell me which one comes first. Let me make sure that I enforce that notion. Who comes first? So I will say here, E goes to E plus T, or E minus T, or T, okay? And then I say, okay, T goes to T times F, or T divided by F, or F. Now what this does is, by factoring this part, can actually put the associativity rule in place, meaning now E plus T, what I am guaranteeing is that E plus T, this T part can be either another addition, or if it is gonna be an multiplication, it's gonna be only in this part. The multiplication is gonna be there. Now, with that, what I am doing is I am actually at this, the idea here is that I am kind of forcing which operators, the associativity of the operators here. I'm saying, okay, E plus T will say, or E minus T will say, T is gonna be, so there will be always something plus, and the multiplication is gonna be on T and F only, and T and F can be only T or F, which is gonna be forced by which is gonna have a parenthesis in them to have any other expression. So this is, if I didn't have this one, it will be very restricted, but this says multiplication can be done by multiplication and another F, which is either an ID or a number, or it can be with something that has parentheses around it. So this would actually enforce this associativity rule for multiplication and addition. Of course, this has to be done carefully. So you need to be smart to actually smart enough to write these things. So it requires some time and effort to actually write it. It's not obvious how you would actually do this one. But it's not always possible to remove ambiguity this way. This is not always possible. So when there is when it is not possible, engineers say, okay, you know, it is good, or scientists say, I want to have a rule that governs everything. So this is my grammar. Engineer says, okay, I have some exceptions, and I'll put those exceptions in place. So, for example, if you have two rules that actually conflict with each other to reduce conflict, you would say, okay, I ask you to order them, and that order would mean something. So I can use the order. I would say, okay, I'll choose the one on the top. Seems to be ridiculous because now everything changes, because grammar now has another kind of meaning implanted into it. Not obvious, but if you know what you are doing, and if it is easy to explain what that order does to your grammar, instances of your grammar or your language, then it might be fine. And this we'll see this from time to time. If you recall, we said a grammar is ambiguous if leftmost and rightmost derivations are actually are the same. Okay. And operator associated with it, we talked about it. Okay, let's look at a problem that is I mean, other than operator associativity, the way that we would actually order the operations in an expression, there are some other ambiguities like this dangling else ambiguity. This is a case where you have statement goes to if expression in parentheses then statement, or if expression then statement else statement, right? So in this case, the question is, for this input, which else does this belong to, right? So this is a valid instance of this thing. When you actually do a derivation of this, a leftmost and a rightmost derivation, you see two different versions of it. The leftmost derivation, I think, gets this one, and this is the rightmost derivation, or the other way around. So this would mean that actually I will have a shift reduce conflict in this thing. So how do we resolve? So again, now our engineering kind of let's say side comes into place. So we call ourselves computer engineers in Turkey, but sometimes actually what we are doing is we do computer science. The science and the engineering thing kind of sometimes helps each other, of course, most of the time. And in this case, our engineering side says, okay, I'm going to put exceptions. Why? Because it's practical. I want to solve the problem. I want to solve it, and I want to find the best solution, or not necessarily the best, but the most optimal for the given circumstances. And algo people, C++ people, associate this else with the clauses if. Or they say, okay, otherwise use blocks, description of blocks. This is algo 60s C and C++. We are going to see later what this moduli is, and Ada, this algo 68 moduli and Ada, they use an explicit delimiter to end every condition. They say, okay, I don't care about this thing. I want to have an end if for every if, so that I know where things are. Okay, why do these people actually don't do something like that? They could have done it, but that will be too restricting. Another end if, writing another end if. Again, this is engineering side of the things that is talking about. So they think that this is the most optimal one, and these people think that this is the most optimal one. In Java, they rewrote the grammar and restrict what can appear inside the nested if statement. Okay, so there are alternative approaches to this one. There are some formal ways of actually removing ambiguity, which is called factoring. If you have an ambiguous grammar, S goes to, for example, S goes to if B then S, and S goes to if B then else S, else S. The factoring will say, okay, I will say if B then S and Z, so I will actually factor this part, and then I will define what these Z's are again. So this would actually enforce some of these ambiguity removal. So I'm not going to go through the factoring. This is out of scope of this course, but be aware that there is such a thing. But these are not, I mean, these are methods, just some methods to actually do things that you, I mean, to come up with ambiguous grammar, but these are just tools. They are not algorithms for sure that will take any ambiguity and result in an unambiguous grammar. Another one is a substitution and so forth. I'm not going to go into the details. So this is what I want to say about the context-free grammars to define syntax in two parts. One part is they are kind of interlaced with concrete and abstract syntax almost at the same time, but we haven't. So we said, okay, most of the things in this description should be done on the concrete syntax, and then we would add some more to it for abstract syntax. And this is now this concrete syntax can be easily described by context-free grammars, not necessarily for everything, but some of these things. And in some case, okay, let's see. Moreover, what you would have is you would have some restrictions on these context-free grammars from practicality perspective. So having an algorithm to implement them, this shift-reduce parser or this top-down parsers that we discussed, LL and LR parsers, and they would not like, those algorithms will not like they would not like ambiguity, that's for sure, and they cannot express, or the things that they can actually parse, they are not the whole set of CFGs. It's only a portion of CFG. And it turns out that in practice, most of these algorithms, especially the shift-reduce algorithm, is powerful enough to capture all our needs, mostly at least, most of our needs in describing the concrete syntax. Now, one of the advantage of this shift-reduce parser is also the building of the parse tree comes more or less as a byproduct, free. So this is also good. Now, BNF that we used, this Bacchus NOR form that we used, is a simplistic one. It's ideal one, but there are some issues, some inconveniences with it that engineers probably don't like much. So for that, we actually have this extended BNF, eBNF. And what we do is, if you have optional parts on the right-hand side, similar to regular expressions, we can use brackets. This is just notational convenience. So instead of writing with ors and so many things, then you actually put these optional parts with using the square brackets. Okay, and you can use braces on the right-hand side of these production rules to indicate indefinite, repeat, or none. So this is 0 or more repeats. And you have the multiple choices, but you can have these multiple choices for, let's say, a little bit more convenient. For example, in this case, the second example, the first example here, I say, okay, what is going on here? I know that term and factor in between might have multiplications and so forth. This would have been done t goes to t star f or t divided by f or t modulo f, right? So you would need to write 3 of these multiple options. Now, instead, if this is just these are the changing ones, you can actually put them within parentheses saying that these are the optional ones. This can be either this or that or that. Okay, and then there are some, so you can see now that these are the meta symbols. These are called meta symbols. They are not terminals, they are not non-terminals. They are some meta symbol belonging to this meta language, the grammar. And with this one, a little bit easier, conveniently. Okay, so this is called eBNF. And the parsers, let's say Bison or some similar parsers, will actually use this extended BNF, all right, because they are easier to manipulate. So just to kind of wrap up, where am I? What time is it? Okay. There are, of course, more capable or more powerful grammars out there. And these are the context-sensitive grammars. The production rules have the form of something like this. If you recall, before we were only doing a non-terminal symbol going to something. Now what we are doing is we have this thing conditioned upon or context driven upon alpha and beta here. So these type of things. It says if you have alpha happened and beta will happen, then you can say A can be W. So this is depending on the context. So alpha and beta depends the context of A's replacement with W. So these are called context sensitive grammars. And however, these are not easy to, I mean, there are, even with the context-free grammars, we have seen that the parsers for such a grammar is difficult. There are cases where we cannot actually do it. Here, the emptiness of a language even in this case is an undecidable problem. So the decision is if this language is empty or not is undecidable. So these are difficult problems. So difficult to parse things. So there are probably instances, simpler instances that you can hopefully do something about, but not necessarily. Now, where can we use these? What is this context-sensitive grammars do? For example, you can think about defining typing rules. For example, type systems. Your typing rules depends on context, right? So a given literal or given number or a given parameter in a dynamically typed and type inference system could actually require these type of context sensitive grammars. Now, of course, you could define, let's say, a typing system or some relationships for a typing system as context sensitive grammars, but what happens usually is that the complexity of parsing such a grammar is so big, and the advantages that a grammar to explain such a thing is not necessarily as proportional to that complexity. People tend to do these things, this part of the things, instead of using a grammar, they actually just write rules for those, and that's it. So they write books for explaining what is what, instead of writing a context-sensitive grammar. So, and there are even unrestricted grammars. These are the equivalent to Turing machine. And when you look at actually from the complexity let's say, if you define let's say a program as a string of characters, right? So this is your empty space. This is infinitely big. Not necessarily, I mean, it's not practical to be infinitely big, but let's say this can be very, very large space. So a regular grammar, the Lecture, will remove some of these things. So it will say, okay, these parts, they are not good for this language. So for example, when you say, I don't want to have, let's say, I don't know what, for example, question mark in my symbols, then you are actually getting rid of a lot of things, right? Or for example, let's say 1A1, for example. This string is not an identifier. Therefore, any such instance of a program that has this 1A1 will actually be rejected. So you reject a big portion of this thing with a regular grammar or a Lecture. And then comes your other part, the context-free grammar. This is the parser. This is the concrete syntax, and it will already eliminate portions of your whatever your Lecture is parsing, right? So if, for example, your Lecture may pass A, B equals C, but C doesn't like this one. C says, okay, there is no rule, syntax rule for this one. So therefore, it will be actually removed, or rejected. So the remaining ones will be actually part of the context-sensitive program or grammar. This is the type checker, for example. As I said, we don't usually use context-sensitive grammars for this, but you can think that this is the part of actually context-sensitive grammars, type checkers. And then even that is not going to be a correct program, because a program at the end, even if it goes through actually context-sensitive things, it may still crash. It may still not run as you want it. So a correct program with the intended semantic from you cannot be captured even with none of these things. So there are things that will not be captured by actually this side here. So this part may pass all things that you know of, but still may not be correct. So this means that your grammars, your parsers, your type checkers, and so forth will give you a perfect program that will do what you intended to do. There is no guarantee usually. And people try to, of course, let's say, limit or make this area smaller and smaller. So if this area is smaller, then it's good, right? Or if this area is empty, then you can say, okay, hey, I can guarantee that my program is correct. But there is no such thing because, again, this part of the implementation or this part of the description is not complete. And we have seen that this is not, we'll see that there will be a lot of things that will not be possible there, unless you want to limit things very, very well. Okay, so I think we are out of time. Any questions? So if there are no questions, then I'll be seeing you next Monday, hopefully. Have a nice day.